I'm going to show you a famous proof by the Swiss mathematician Leonard Euler, E-U-L-E-R, and this is one of the most clever proofs I've ever seen, and I hope I can explain it well. The basis of this proof is someone wrote to Euler and said, I noticed that if I take a number like 8 and I write it as the sum of a bunch of numbers, for instance, 8 could just be the number 8, or I could write it as 1 plus 7, and if I'm not allowed to repeat numbers, I can't use 4 plus 4, I could use 2 plus 6, I can use 3 plus 5, I can use 1 plus 2 plus 5, and 1 plus 3 plus 4. And they notice that there are exactly 1, 2, 3, 4, 5, 6 ways of writing the number 8 as the sum of distinct positive integers. Well, what if I try to find a number of ways of writing the number 8, but this time I'm allowed to use repeats. However, I'm not allowed to use any even numbers. Well, this is going to change things now. So 1 plus 7 is still valid, and 3 plus 5 is still okay. But now I can't use some of these other ones like 2 plus 6, but I can use repeated numbers now. So now I'm able to use 1 plus 1 plus 1 plus 5, and something like 1 plus 1 plus 3 plus 3, and something like 1, 2, 3, 4, 5 ones, and a 3, and even 1, 2, 3, 4, 5, 6, 7, 8 ones. And this one, 1, 2, 3, 4, 5, 6, also has 6 ways. 6 ways. And the conjecture is that Euler is going to prove to become a theorem is that this is always going to happen. If you pick any number, like 8, and you figure out all the ways of writing it as the sum of distinct positive integers, and then if you do it again, but you write it as the sum of odd numbers, restrict yourself to odd numbers, but repeats are allowed, that the number of ways are going to be equivalent. And someone actually wrote to Euler and said, can you prove this? And Euler figured out a very creative proof, which I'm going to try to take you through. In math, here's some prerequisites. In math, we learned that to multiply polynomials together, like something like this, they teach us what we sometimes call FOIL, when we multiply these together. And we multiply the outers, and we multiply the inners, and we multiply the lasts together. And we get 4 terms, and those terms, some of them have the same coefficient, have the same variable part, so we can combine like terms. So that's FOIL. But what if we have a much more complicated thing? Like, what if I'm multiplying a whole bunch of binomials together? So here I'm trying to multiply 4 different binomials. Well, we can't use FOIL anymore, but the idea behind FOIL is that each of these 4 terms has one thing from the first set of parentheses and one thing from the second parentheses. And the 3x has the x from the first set of parentheses and the 3 from the second set of parentheses, and the 2x has the x from the second parentheses and the 2 from the first, and the 6 has the 3 and is composed of the 3 and the 2. And that's what happens when you have a much larger thing. There are 4 sets of parentheses here. There's going to end up being 16 terms, and each term is going to have something, one thing from this parentheses, one thing from this parentheses, one thing from this parentheses, and one thing. So for instance, one of the terms is going to be A, C, E, G. That's going to be the one that you get by multiplying, choosing the A, the C, the E, and the G. Another term, just to make up another random one, is going to be B, C, E, H, somewhere in there. Now usually if you're going to do something like this, you want to do it in a logical order so you don't leave any out or count any twice. But that's kind of the idea behind this. Every term is going to have something from each parentheses. So for instance, there's going to be one that's A with the D, with the F, with the G. And there's going to end up being 16 of them. If I was doing it in some kind of logical order, the last one would probably be choosing the B from the first, the D, the F, and the H. which is kind of like the lasts. This is kind of like the first. But I don't think I'm going to be able to make up a 16-letter word that describes all the different combinations the way you can do with FOIL. So FOIL is basically picking one thing from the first set of parentheses and one thing from the second and doing all four ways of doing that, whereas with a bigger polynomial. And if I have an even bigger thing, imagine I have like a plus b plus c plus d, e plus f plus g plus h, I plus j plus k plus l. Let's say I have these 4-term things. The same sort of thing is going to happen after I multiply this whole thing out. One of the terms is we're going to pick one thing from each set of parentheses. So I pick, let's say, the a and the f and the I. That's going to be one term. Whereas I could also pick the a with the e with the I. And somehow I could pick the c with the g with the k. This thing would have 64 terms in it because there's 4 things. I have to pick any of 4 things from each of them. But that's the idea that we have to. We need this as a prerequisite for this. It's the main prerequisite for this this proof that Euler's going to do. Okay, so let's look at what Euler does. Euler says, I have an idea about a very strange polynomial. 1 plus x times 1 plus x squared times 1 plus x to the third times 1 plus x to the fourth. And this is actually going on forever. So to multiply this out would require infinite number of terms. But to give you an idea of what would happen if you multiplied this out, one of the terms you would get by multiplying 1 times 1 times 1 times 1 all the way down the line. So 1 would be one of the terms. I could also get a term by multiplying x in the first parentheses and using the 1s from the rest of them. So that would just be 1x. I could also get one by using the 1 from the first and the x squared from the second, and then 1s from there on. I could also get one by using the 1, and the x cubed and 1s from then on. But here's where it gets interesting. I don't have to use this first one. What if I use this x from the first parentheses, this x squared from the second, and then 1s from then on? I'll get 1 times x squared. And these things can be combined. Remember, 1x to the third plus, when you multiply two things like this, we add the exponents. I'm going to actually write it as 1 plus 2, which becomes 2x to the third. So the coefficient on the x to the third is going to be 2. The coefficient on x squared is just 1. The coefficient on x is just 1. Now, it's not so obvious what's going to happen down the road when I get to, eventually, the x to the 8th to the x to the 8th term. And what would the coefficient be? Well, to give you a feel for this, I'm going to write this out again. Plus x to the fourth, I'll just go up to 1 plus x. Okay, and it actually goes on forever, but for our purposes, this should work. So one way of getting x to the 8th is to use the 1s and the x to the 8th term from this parentheses, and 1s from then on. So I would get 1x to the 8th. Another way, erase this. Another way to get x to the 8th would be to use the x, the 1, the 1, the 1, the 1, the 1, the x to the 7th, and then 1s from then on. So I'm going to write 1 times x to the 1 times x to the 7th. Another way to get x to the 8th would be to use the 1 and the x squared, and the 1 and the 1 and the 1 and the x to the 6th, and then 1s from then on. And if I kept doing this, I would end up with x to the 3rd times x to the 5th is a way of getting x to the 8th. And even if I use the x squared, the 1, the x to the 5th, the 1, the 1s from then on, I could get x to the 1 times x to the 2 times x to the 5th. And there's one more, which would be 1 times x to the 1st times x to the 3rd times x to the 4th. Notice there are 1, 2, 3, 4, 5, 6 of these. The answer is 6. But remember, that 6 also means if I combine this, I get x to the 8th, but I could also write it as x to the 1 plus 7. And this one I could write as 1 times x to the 2 plus 6. And this one I could write as 1 times x to the 3 plus 5. And this one I could write as 1 times x to the 1 plus 2 plus 5. And this last one I could write as 1 times x to the 1 plus 3 plus 4. In other words, these are precisely the 6 ways of writing 8 as a sum of distinct integers. And this polynomial, this polynomial here, has the special property after you multiply it out that when I multiply it out, I get 1 plus 1x plus 1x squared plus 2x to the 3rd plus somewhere down the line 6x to the 8th. And in general, for any random or arbitrary n value, this number is going to be, this coefficient is going to be the number of ways of writing n as a sum of distinct integers. So we created this polynomial that if you multiply it out would have this special property. Its coefficients would have this special property. So that's pretty cool, although it doesn't seem to lead us anywhere yet. But it's going to. Euler now says I have a second pretty involved polynomial. And this one looks like this. And unlike that last polynomial where it was a bunch of binomials being multiplied together, this goes on forever, and it gets multiplied by one that starts with 1, then goes to x to the 3rd, then goes to x to the 3 plus 3, then goes x to the 3 plus 3 plus 3, and that one goes on forever. And this string of polynomials actually goes on forever. The next one's going to be 5. It's going to always start with the next odd number. And there's going to be an infinite. So this is an infinite product, and each one of these is infinite. And Euler says that if you were to multiply this gigantic monstrosity out, you would get 1, because that's what you get if you multiply all the 1's together down the line, plus 1x to the 1st. That's what you'd get if you multiplied this x to the 1st times 1 down the line, plus 1x squared. That's the one you get if you take the x to the 1 plus 1 and multiply it by 1's all the way down, plus 2x to the 3rd. It's 2 because you could get it by doing x to the 1st times x squared times 1 times 1 times 1 times 1, or you could get it by doing 1 times x to the 3rd times 1 times 1 times 1 down the road. So again, I can get x to the 3rd term by using this guy with 1's everywhere else, or I can get it by using this oops, just realized that was a mistake. There's no way to get this. However, what I should have said was x to the 1 plus 1 plus 1. So if I used this guy with 1's from then on, I'd get this was right, it still is 2, but for this reason. And somewhere down the line, there's going to be an x to the 8th term, and it's going to need a coefficient. Well, where is that coefficient going to come from? Well, one way is if I use 1 from the first parentheses, x to the 1 from the second, 1 from the third, 1 from the fourth, 1 from the fifth, 1 from the sixth, use x to the 7th from the 7th parentheses, oops, strike that, x to the 1 from the first parentheses, 1 from the second parentheses, 1 from the third parentheses, but the x to the 7th from, there is a fourth set of parentheses, is 1 plus x to the 7th plus going on, and then 1's down the line, so it'll be x to the 1 plus 7, which is x to the 8th. I could also instead use this 1 with this x to the 3rd and this x to the 5th. If I use this, oops. If instead I use the 1 from the first parentheses, the x to the 3rd from the second parentheses, the x to the 5th from the third parentheses, and then 1's down the line, I get x to the 3 plus 5, which is another 1x to the 8th. I could also have used from the first set of parentheses the 1 plus 1 plus 1, a 1 from the second set of parentheses, and x to the 5th from the third set of parentheses. That would be x to the 1 plus 1 plus 1 plus 5, which is another x to the 8th. I could have also used an x to the 1 plus 1 from the first set of parentheses, and x to the 3 plus 3, I haven't used that yet, from the second set of parentheses, and 1's down the line to get x to the 1 plus 1 plus 3 plus 3 is a 1x to the 8th. I could have also used the one with 5 1's from the first set of parentheses, and the one from the second parentheses was just the 3, and then 1's down the line. 1, 2, 3, 4, 5 plus 3 equals 1x to the 8th. And finally, I could have used, if I had wrote out a few more terms of this first set of parentheses, one of them was going to be x to the 1 plus 1, 3, 4, 5, 6, 7, 8, and then 1's from then on, which would be x to the 1, 2, 3, 4, 5, 6, 7, 8, which is also 1x to the 8th. Notice that it is 6x to the 8th, 6 again. And as you can see, these are the ways of writing 8 as a sum of odd integers where repeats are allowed. So we created these two pretty awesome polynomials. Now the trick is for him to show that those two polynomials are equivalent to each other. And that seems like a very difficult feat. But here's the way he does it. He takes the q polynomial. I'm just add these, instead of writing 1 plus 1 plus 1, I'll write x to the 3rd, x to the 4th. That goes on forever. The other one is 1 plus x to the 3rd plus x to the 6th plus x to the 9th going on forever. And then 1 plus x to the 5th plus x to the 10th going on forever. Each of these is what's known as an infinite geometric series. And I'm going to assume that people watching this know that the sum of an infinite geometric series is a over 1 minus r. The infinite series is written as a plus ar squared plus going on forever, and it equals a over 1 minus r, where a is the first term and r is the common ratio. So in this case, it's 1 over 1 minus x. And this is also a geometric series because each term is x cubed times the one before. So it's 1 over 1 minus x cubed. And the next one is going to be 1 over 1 minus x to the 5th. And that's going to go on forever. So this is getting sort of tamed. What Euler then says is, what if I multiply top and bottom? Because if you multiply top and bottom by the same thing, it's like multiplying by 1 minus x squared times 1 minus x to the 4th times 1 minus x to the 6th, all the even ones. And this bottom is also going to get that. What would that do? Well, in the numerator, each of these is what's called the difference of perfect squares. So 1 minus x squared can be factored to 1 minus x times 1 plus x. And 1 minus x to the fourth can be factored to 1 minus x squared, 1 plus x squared. And 1 minus x to the sixth can be factored to 1 minus x cubed, 1 plus x cubed. And now we can do some canceling. I can cancel this 1 minus x with this 1 minus x. And this 1 minus x squared can get canceled with this one. And this 1 minus x cubed can get canceled with this one. And ultimately what ends up getting canceled, all the 1 minus x to the, or all the 1 minus x to the odd powers get canceled out with these guys, and all the 1 minus x to the even powers get canceled out with these guys, and all that remains after everything is canceled out are the 1 plus all the positive integers, which is exactly what Euler calls p of x from before. So that's one of Euler's great proofs. It doesn't rely on very complicated math, but it's ingenious, and I hope you like that proof. Thanks for watching.